Welcome to this video on solving LeetCode problem number 882, titled Reachable Nodes in Subdivided Graph. In this session, we'll break down the problem, explore the key concepts, and guide you through an efficient approach to solve it. Let's dive in. In this problem, we are working with an undirected graph, which means that edges between nodes can be traversed in both directions. The graph is described by n nodes and an array of edges, where each edge connects two nodes, u and v, and has a parameter c and t. This c and t tells us how many additional nodes can be created by subdividing the edge. For example, if you have an edge 0, 1, 4, it can be broken down into 5 smaller segments, represented as 0-0_1-0_2-0_3-0_4-1. Additionally, you are provided with a value max moves, which is the maximum number of steps you can take starting from the first node, node 0. The goal is to figure out how many unique nodes you can reach within these constraints, including the original graph nodes and any subdivided nodes created by breaking down the edges. Now, let's talk about the input and output formats. The input consists of 3 main components: the number of nodes, n, the list of edges, where each edge specifies 2 nodes u and v and the numbers c and 4 subdivisions, and the value max moves, which is the maximum number of steps you are allowed to take starting from node 0. The output is a single integer representing the total number of unique nodes you can reach in the subdivided graph. This includes both the original nodes and any subdivided nodes along the way. To make this clear, let's look at an example. In the first example, we have 4 nodes, and the edges are described as 0, 1, 4, 1, 2, 5, 2, 3, 1. The maximum moves allowed are 7. The edge 0, 1, 4 gets subdivided into 0-1-1-0-2-0-3-0-4-1, and similarly, the other edges are subdivided too. Starting at node 0, you can use 4 moves to traverse the entire first edge and reach node 1. With the remaining 3 moves, you can explore part of the second edge and reach some of its subdivided nodes. The reachable nodes include all the original nodes 0, 1, 2, 3 as well as many of the subdivided nodes like 0_1, 0_2, 2_1. Altogether, this gives a total of 13 reachable nodes. In the second example, the graph has 5 nodes and edges given as 0, 1, 10, 0, 2, 1, 1, 3, 2, 1, 4, 3, with a maximum of 6 moves. Here, the edge 0, 1, 10 has up to 10 subdivisions, but you may not be able to explore all of them due to the move limit. The edge 0, 2, 1 creates a short path, making it possible to quickly reach node 2. Starting at node 0, you can use 1 move to reach the first subdivision of 0, 2, 1 and node 2. The remaining moves allow you to partially explore edges 0, 1, 10 and 1, 3, 2. The total count of reachable nodes is 9, including the original nodes 0, 1, 2, 3, 4, and several subdivided nodes. Finally, let's consider the constraints. The number of nodes n in the graph can range from 1 to 300, and the number of edges is limited to the smaller of either 10,000 or the total possible edges in the graph, which is n*(n1/2). Each edge must be defined with exactly 3 values, u, v, c and t, where u and v are distinct nodes, and c and t is a positive integer that can go up to 10,000. The maximum moves, max moves, is a non-negative integer that can be as large as 1 billion. Lastly, it's important to note that the graph is always connected, meaning there's at least one path between any pair of nodes. These constraints ensure that the problem is well defined and solvable within the given limits. To solve the problem of calculating how many nodes are reachable in a subdivided graph, we evaluated several approaches. The first is the brute force approach, where we explicitly construct the entire graph, including all subdivided nodes. For each edge, u, v, c and t, this means creating c and t intermediate nodes and expanding the graph fully. While intuitive, this approach comes with significant drawbacks. Constructing the expanded graph alone has a high time complexity of (e*c and t, where e is the number of edges and c and t represents the average number of subdivisions per edge. Traversing this expanded graph with techniques like BFS or DFS further increases the computational cost, resulting in a worst-case complexity of (n plus e*c and t, (2). Additionally, the memory overhead involved in explicitly storing these subdivided nodes makes this method impractical for large inputs where the number of nodes, edges, or subdivisions can scale up to the order of 10 to the power of 4. A more efficient alternative is the optimized approach using Dijkstra's algorithm. Here, instead of explicitly constructing the subdivided graph, we treat the number of subdivisions, CNT, as weights on the edges and use a priority queue to guide the traversal. Dijkstra's algorithm is particularly well suited for this task as it explores nodes in the order of the fewest moves used, ensuring efficiency while avoiding redundant exploration of paths. In the optimized approach, we use a priority queue to explore nodes based on the remaining moves available. By tracking the maximum moves left after reaching each node, we can ensure that redundant exploration is avoided. For each edge, we calculate how many subdivided nodes are reachable from both endpoints within the remaining moves. These reachable counts are then summed up, along with the nodes that are reachable directly within the original graph. This method has a much more efficient complexity. Constructing the graph takes O, E, and Dijkstra's algorithm runs in O, n plus E, asterisk log, n, where n represents the number of nodes and E the number of edges. This efficiency makes it suitable even for larger inputs. However, this approach does require careful bookkeeping of the moves left at each node to ensure correctness. An alternative method we considered involves heuristic-based search, where edges with higher subdivision counts, CNT, are prioritized. While this greedy method is faster and simpler, it lacks the guarantees of optimality provided by Dijkstra's algorithm. Ultimately, the optimized approach using Dijkstra's algorithm strikes the best balance between time complexity, memory efficiency, and accuracy in solving this problem. The key insight that makes the optimized approach effective is that the subdivided nodes don't need to be represented explicitly. Instead, their counts can be calculated mathematically during traversal, significantly reducing memory usage. Dijkstra's algorithm plays a crucial role here, as it ensures that we explore nodes in the most move-efficient order, prioritizing paths that minimize the moves used. Additionally, by tracking the remaining moves at each node, we avoid unnecessary computations while guaranteeing correctness. This approach is efficient, running in O, n plus E, asterisk log, n, and avoids the pitfalls of brute force methods, which are infeasible for larger inputs due to their high time and space requirements. Compared to heuristic-based search, this method is more accurate, as it guarantees the correct count of reachable nodes. In summary, the optimized use of Dijkstra's algorithm, combined with the mathematical interpretation of subdivided nodes as edge weights, offers the best trade-off. It ensures scalability, minimizes memory overhead, and provides an accurate solution to the problem of counting reachable nodes in a subdivided graph. In this problem, we are tasked with finding how many nodes, including both original and subdivided nodes, can be reached within a given number of moves in a subdivided graph. The graph is represented as an edge list, where each edge between two nodes is subdivided into multiple segments, introducing intermediate nodes. However, instead of explicitly creating these intermediate nodes, we can logically handle them during graph traversal by treating the edge weight as the number of subdivisions. To solve this, we need an efficient traversal strategy, and Dijkstra's algorithm is a great fit since it allows us to prioritize paths with the fewest moves. A key idea is to adopt a greedy approach, always exploring nodes that require the least moves first, which helps maximize the total number of reachable nodes within the given constraints. To implement our solution, we need to carefully choose and organize our data structures. First, we represent the graph using an adjacency list, where each node points to its neighbors along with the weights of the edges connecting them. This representation is memory efficient and easy to traverse. Next, a priority queue or min-heap is crucial for implementing Dijkstra's algorithm, as it allows us to always process the node with the smallest number of moves first. Additionally, we maintain a visited dictionary to track the maximum remaining moves available upon visiting each node. This prevents redundant or suboptimal visits to the same node. The algorithm starts by initializing the graph from the input edge list, where each edge weight is set as the number of subdivisions plus 1. We then set up the priority queue with the starting node, ensuring that we have all the tools in place for an efficient traversal. The traversal process begins by extracting the node with the least number of moves used from the priority queue. If we have already visited this node with more remaining moves in the past, we skip it to avoid redundant computation. For each neighbor of the current node, we we calculate the moves required to reach it. If the neighbor is reachable within the move limit, we update the priority queue in the visited dictionary with the new state. Additionally, for subdivided nodes along the edge, we calculate how many of them are reachable based on the remaining moves and increment the count accordingly. Once the traversal is complete, we count all the reachable original nodes and, for each edge, calculate the reachable subdivided nodes from both endpoints. These contributions are summed up to get the final result, which represents the total number of reachable nodes, including both original and subdivided nodes. To optimize this approach, we leverage several key techniques. First, we avoid explicitly creating subdivided nodes for each edge, instead calculating their reachability on the fly during traversal. This saves both memory and computation. Additionally, we implement early stopping in Dijkstra's algorithm. If the remaining moves are not sufficient to reach any neighbors, further exploration from that node is halted. Another important optimization is the calculation of edge contributions, where we account for reachable subdivided nodes from both endpoints, ensuring no double counting occurs. When analyzing the time complexity, constructing the graph takes O(E), where E is the number of edges. Dijkstra's algorithm runs in O(V plus E) log V, where V is the number of original nodes, and the edge contribution calculation is O(E). This results in an overall complexity of O(V plus E) log V. The space complexity is dominated by the graph representation, priority queue, and visited dictionary, giving us a total of O(V plus E). Finally, we address some critical edge cases to ensure robustness. For isolated nodes, we handle scenarios where certain nodes are unreachable. When the move limit is 0, we confirm that the algorithm correctly returns only the starting node, if reachable. For edges with large subdivision counts, we avoid explicitly creating the intermediate nodes, ensuring efficiency even with high values of CNT. Let's consider an example to solidify these concepts. Given edges between nodes 0, 1, and 2 with varying weights and a maximum move limit of 5, we start at node 0 and traverse the graph. From node 0, we reach node 1 and its subdivided nodes, then proceed to node 2 and its subdivisions. By counting all reachable original and subdivided nodes, we determine that the total reachable nodes in this case are 7. This example highlights how the algorithm carefully balances efficiency and accuracy to solve the problem. Here, we start by importing the heap module, which will help us implement a priority queue for Dijkstra's algorithm. Then, we define the reachable nodes function that takes 3 inputs, edges, representing the graph, max moves, which is the maximum number of moves allowed, and n, the total number of nodes. Inside the function, we first construct an adjacency list called graph, where each node points to its neighbors along with the weight of the edge between them. This adjacency list is built using a dictionary comprehension and a loop over the edges. Next, we initialize the priority queue PQ with the starting node, represented as a tuple where the remaining moves are stored as a negative value for the heap to function as a max heap. We also create a visited dictionary to track nodes and the maximum moves left when they are visited, and we initialize reachable_count to 0 to keep track of the number of reachable nodes. The main loop processes nodes from the priority queue. Here, we pop the node with the most remaining moves, and since the heap stores negative values, we negate moves_left to get its actual value. If the current node has already been visited with more remaining moves, we skip further processing. Otherwise, the node is marked as visited, and we increment the reachable_count since this node is now reachable. Afterward, we prepare to explore its neighbors. For each neighbor of the current node, we check if visiting it with the remaining moves would result in a better state. Specifically, we ensure that either the neighbor hasn't been visited yet, or the moves left after traveling to it exceed the moves already recorded for that neighbor. If the remaining moves are sufficient to reach this neighbor, we push the updated state into the priority queue, reducing the moves left by the cost of the edge and one additional move needed to traverse it. Once we've processed all nodes, we calculate the reachable subdivided nodes. For each edge in the graph, we check how many of the subdivided nodes along that edge can be reached based on the moves remaining for both endpoints of the edge. The minimum of the sum of these moves and the total number of subdivided nodes along the edge is added to reachable_count. Finally, we return reachable_count, which represents the total number of nodes and subdivided nodes that are reachable within the given constraints. Here, we begin by defining our solution class and the main method, Reachable nodes. The method takes three inputs: the edges of the graph, the maximum number of moves allowed, and the total number of nodes. To represent the graph, we use an adjacency list where each node maps to its neighbors and the weight of the edge connecting them. This is achieved using a nested hash map structure. We iterate over the edges to populate this adjacency list, ensuring the graph is bidirectional by mapping each edge for both nodes. Next, we set up the priority queue for Dijkstra's algorithm, which helps us process nodes with the most remaining moves first. Each element in the queue is an array containing the remaining moves and the current node. We also initialize a visited map to track the maximum remaining moves when visiting each node, and a variable reachable count to count the nodes we can reach. As we process the priority queue, we repeatedly pull the node with the most remaining moves. If the current node has already been visited with equal or more remaining moves, we skip further processing for efficiency. Otherwise, we update the visited map with the node and its remaining moves, and increment the reachable count since this node is reachable. Then, we explore its neighbors by iterating through the adjacency list. For each neighbor, we calculate whether it's worth visiting based on the remaining moves after accounting for the edge cost. If visiting this neighbor is feasible and provides more remaining moves than previously recorded, we add it to the priority queue with the updated moves. After processing all nodes in the priority queue, we calculate the additional reachable nodes in the subdivided edges. For each edge, we determine how many subdivided nodes can be reached from both endpoints, constrained by the remaining moves from each endpoint. We sum up the reachable subdivided nodes, ensuring we don't exceed the total number of subdivisions for that edge. Finally, we return the total reachable count, which includes both fully reachable nodes and the reachable subdivided nodes in the graph. This completes the implementation of the solution, leveraging Dijkstra's algorithm for efficient traversal and calculation of the reachable nodes within the constraints. To solve this problem, let's start with a basic example. We are given a graph with edges 0, 1, 4, 1, 2, 3, 0, 2, 5, a maximum of 6 moves, and 3 nodes. First, we construct the graph as an adjacency list, where each node is a key, and its neighbors with their respective edge weights are the values. This results in the graph structure 0, 1, 4, 2, 5, 1, 0, 4, 2, 3, 2, 0, 5, 1, 3. Next, we initialize the priority queue with the starting node 0 and 6 moves remaining, PQ equals -6, 0. We also create an empty visited dictionary to track the maximum moves left when visiting each node, and a reachable _count variable to keep track of all reachable nodes and subdivided nodes. At this stage, visited is, and reachable _count is 0. Now we process each node in the priority queue. Starting with node 0, we pop it from the queue, leaving us with 6 moves. We mark node 0 as visited with 6 moves left and increment the reachable _count to 1. Then, we explore its neighbors. For neighbor 1, we calculate the remaining moves as 6, 4, 1 equals 1 and push it into the queue. Neighbor 2, however, has no moves left, so we skip it. Next, we process node 1 with 1 move left. We mark it as visited and increment the reachable _count to 2. Since there are no valid moves left for its neighbors, we proceed to count the reachable subdivided nodes along each edge. For the edge 0, 1, 4, nodes 0 and 1 contribute min, 6 plus 1, 4, equals 4 nodes. For the edge 1, 2, 3, nodes 1 and 2 contribute min, 1 plus 0, 3, equals 1 node. Finally, for the edge 0, 2, 5, nodes 0 and 2 contribute min, 6 plus 0, 5, equals 5 nodes. Adding these to the reachable _count gives a total of 12. Thus, the output for this example is 12. Now let's consider an edge case where some nodes are isolated. The input graph has edges 0, 1, 2, 1, 2, 1, with a maximum of 2 moves and 4 nodes. First, we construct the adjacency list, resulting in the graph 0, 1, 2, 1, 0, 2, 2, 1, 2, 1, 1, 3. Notice that node 3 is isolated, as it has no connections. We initialize the priority queue with the starting node 0 and 2 moves left, PQ equals -2, 0. The visited dictionary is empty at this point, and the reachable _count is set to 0. Starting with node 0, we pop it from the queue and find that we have 2 moves left. We mark node 0 as visited and increment the reachable underscore count to 1. Next, we explore its neighbor, node 1, but find that after spending 2 moves to reach it, no moves are left for further exploration. We then process node 1 with 1 move left, marking it as visited and incrementing the reachable underscore count to 2. From node 1, we add its neighbor, node 2, to the queue with 0 moves left. Finally, we process node 2, marking it as visited with 0 moves left and incrementing the reachable underscore count to 3. At this point, we count the subdivided nodes for each edge. For the edge, 0, 1, 2, nodes 0 and 1 contribute min, 2 plus 1, 2, equals 2 nodes. For the edge, 1, 2, 1, nodes 1 and 2 contribute min, 1 plus 0, 1, equals 1 node. Adding the reachable nodes and subdivided nodes together, we find that the total reachable underscore count is 3 plus 2 plus 1 equals 6. This includes the 3 reachable nodes and the subdivided nodes along the edges. The isolated node 3 does not contribute to the count since it is disconnected from the rest of the graph. Therefore, the final output for this example is 6. To analyze the time complexity of the algorithm, we start by breaking it down into 3 main components. First, graph construction involves iterating through the edges array to create an adjacency list. Since there are edges, this step takes time. Next, the core of the algorithm is a modified Dijkstra's algorithm, which relies on a priority queue to process nodes. In the worst case, all nodes, denoted as n, are processed, and for each node, its neighbors are examined. Since the priority queue requires log v, time for each push or pop operation, and all nodes and edges are visited, this step has a complexity of v plus e log v. Finally, counting the reachable nodes from subdivided edges requires iterating over all edges, leading to a complexity of e. When we combine these components, the overall time complexity becomes e plus v plus e log v plus e, which simplifies to v plus e log v. After understanding the time complexity, let's look at the space complexity. The algorithm's space usage is determined by several factors. First, the adjacency list representation of the graph uses v plus e space, where v is the number of nodes and e is the number of edges. The priority queue, which holds at most 1 entry per node, requires v space. Additionally, the visited dictionary, which stores the maximum remaining moves for each node, also takes v space. Finally, auxiliary variables such as counters and loop variables only contribute a constant 1 space. When we add these together, the total space complexity becomes v plus e. Comparing this to a brute force approach, which would require exponential time and space due to simulating all possible paths, this optimized approach is significantly more efficient, with a time complexity of v plus e log v and a space complexity of v plus e. Continuing with the comparison, the brute force method would involve simulating every possible path from the starting node, up to a maximum of max moves. This could lead to exponential growth in the number of paths, resulting in a time complexity of v max moves, in the worst case. In contrast, our optimized approach leverages Dijkstra's algorithm to process nodes systematically, drastically reducing the computational cost to v plus e log v. This is a huge improvement, especially for larger graphs. The space complexity of v plus e also ensures that the algorithm remains feasible even for graphs with a large number of edges and nodes. By focusing on efficient graph traversal and edge relaxation, the optimized approach avoids the inefficiencies of exhaustive simulation. To better understand the algorithm's behavior, let's analyze the best, average, and worst case scenarios. In the best case, where the graph is sparse with only a few edges and max moves is small, the algorithm processes only a subset of nodes and edges, resulting in small constants for the v plus e log v complexity. In the average case, for moderately dense graphs, most nodes and edges are processed, but the time complexity remains within v plus e log v. The worst case occurs in a fully connected graph, where the number of edges is proportional to v(2). Here, the complexity becomes v squared log v, which is still far more efficient than the exponential complexity of the brute force approach. These cases demonstrate the robustness of the algorithm across different graph structures. Each step, from graph construction to Dijkstra's algorithm and the final counting of reachable nodes, adheres to the mathematical bounds of their respective complexities. Ultimately, the overall complexity of the algorithm is dominated by the Dijkstra's step. While graph construction and the final counting step contribute O, E, each, these are overshadowed by the O, V plus E, log V, complexity of the Dijkstra's algorithm. This makes O, V plus E, log V, the final time complexity of the solution. By leveraging efficient graph representations, priority queues, and systematic traversal, the algorithm achieves both optimal time and space utilization. This ensures it can handle large and complex graphs while maintaining scalability and performance. Let's begin by addressing some common mistakes that arise when solving this problem. One frequent issue is not handling edge weights properly. Remember, the weight of an edge tells you how many subdivided nodes exist between 2 points. If you ignore these weights during your calculations, you risk producing incorrect results. Always ensure you're accounting for how many of these nodes can be visited within the constraints of the problem. Another common pitfall is incorrect usage of the priority queue when implementing Dijkstra's algorithm. If you don't use the priority queue correctly, you might process longer paths before shorter ones, leading to suboptimal results. Additionally, it's important to be mindful of the max moves constraint. This limit means you won't always be able to traverse every edge, so make sure you're subtracting the moves used at each step to stay within bounds. Finally, failing to track visited nodes and edges can result in double counting reachable nodes or edges. Maintain a clear tracking mechanism to ensure accuracy, especially when dealing with subdivided nodes along the edges. Now, let's talk about a few more important points. Using an inefficient graph representation is another mistake to watch out for. For example, using an adjacency matrix for a sparse graph can lead to excessive time and space complexity, making your solution impractical for larger inputs. On the bright side, there are key patterns in this problem that you can leverage. It's essentially a variation of Dijkstra's shortest path algorithm with an additional layer of complexity introduced by subdivided nodes. Understanding how to adapt shortest path algorithms to handle these constraints is a critical skill. Furthermore, interviewers often focus on how efficiently you handle graph traversal under constraints like max moves. Using priority queues effectively and tracking your state carefully can demonstrate your optimization skills. Be ready to discuss edge cases as well, like disconnected graphs, edges with zero weight, or scenarios where max moves is too small to visit any nodes. Lastly, if time allows, talk about trade-offs between different approaches, such as brute force versus an optimized Dijkstra's algorithm, to show your understanding of algorithmic complexity. Next, let's draw connections to some related problems that can help deepen your understanding. Problem number 743, network delay time, also revolves around shortest path algorithms and involves determining reachability within a graph. Similarly, problem number 1631, path with minimum effort, focuses on optimizing effort along a path, which parallels the idea of optimizing moves in this problem. Another great example is problem number 787, cheapest flights within K-stops, which incorporates graph traversal with constraints, just like managing max moves here. Finally, problem number 1514, path with maximum probability, introduces a variation of shortest path problems where you maximize probabilities instead of minimizing distances. Exploring these problems can help you recognize common patterns and apply similar techniques in different scenarios. Lastly, let's consider alternative approaches and their trade-offs. A brute force method, where you explore all possible paths and count reachable nodes, might seem straightforward but is highly inefficient. With exponential time complexity, it becomes infeasible as input size grows. Breadth first search, or BFS, is another option. While it works well for unweighted graphs, it doesn't handle weighted edges as effectively, making it less suitable for this particular problem. The most efficient approach is an optimized version of Dijkstra's algorithm. By using a priority queue, you ensure that paths requiring fewer moves are processed first, resulting in a time complexity of O, E log V, where E is the number of edges and V is the number of nodes. Dynamic programming is another potential approach, where you track the maximum nodes reachable within a certain number of moves. However, this method can be memory-intensive and more complex to implement than Dijkstra's algorithm. Each method has its pros and cons, and understanding these trade-offs is key to selecting the best approach for the given constraints. Great job making it to the end. We covered the solution to LeetCode problem number 882, highlighting the use of Dijkstra's algorithm and efficient graph traversal techniques. Keep practicing graph problems to master these concepts. Thanks for watching. Don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!